Pleasure.
Nice to meet you.
Pleasure.
It's like we're at the end of the team sport.
Yeah, they come to the referee's table.
Yeah.
Karthik is looking like, what?
So your first question will be the easiest one. Please tell us your name.
Hi, everyone. My name is Howard. I'm Vinay.
I'm Alex.
I'm Graham.
I'm Keshav. All right. Everyone ready? Good morning, everyone. My name is Howard, and today my team and I are here to present our solution to the question, what is a college education worth? And so the problem that we addressed is that developments in industry, science, technology, et cetera, require STEM professionals for the future. In order to acquire these STEM professionals, we first need to convince students to go to college. And when many families think about college, they wonder, is it really worth sending my child to college? The skyrocketing price tag might not be worth the bill of debt they get, or maybe they'll receive a useful degree. And so, when we looked at this problem, there were several factors to consider. The first thing we looked at is that all good mathematical models will be able to accurately calculate the cost of attending college. This would include things like the financing options, the size of your family, or the type of college. Next, even if we do manage to convince students to go to college, what guarantee is there that they will actually pursue a STEM major when there are other lucrative fields like business and finance? Maybe students hope to get a nice job over on Wall Street. Thus, we have to look at the pros and cons of different degree programs. And finally, beyond the monetary benefits of going to college, there are both quantitative and qualitative factors that make up an individual's happiness. Therefore, we need to create a model that helps students better plan for their future. Here is just an overview of our model. So for the first part, we looked at these several complex factors that make up the total cost of attending college. This includes things like private versus public universities, the size of your family, the amount of money your family makes. And what we did is we took all of these factors and put them together into a simple equation. This equation is easily personalized to different family situations in order to accurately calculate the cost of attending college. For part 2 of our model, we created another equation that calculates the financial benefit of different degree options. The financial benefit takes into account both job stability and job salary. In this way, we can look at different degree options, compare STEM versus liberal arts, compare attending community college versus a traditional 4-year program. And for the last part of our model, we used a voting and game theory approach to create a tool that helps students determine the best educational pathway based on individual preferences for factors of happiness, like the amount of family time you have, the amount of free time you might get, or the amount of money you make. And now, Vinay will talk about part 1 of our model more in depth. Thank you, Howard. So if you're determining whether something is worth doing, you have to look at both the costs and the benefits of that action. In part 1, we looked at the cost of college. Colleges often advertise a single price of attendance, but often many people pay many different prices to go to college based on individual factors like family size, family income, etc. So part 1, we made some key assumptions. You can read them here. And it's important to note that we considered President Obama's plan to make 2 years of community college free. And all these community college students in part 1 of our model move on to a 4-year institution because it would be pointless to calculate the cost of a free college. And so here is what our model looks like. It's very long and complicated because of all the different factors involved. But its essence is very simple. The payment that a family makes is the cost of attendance minus any financial aid they receive. And so some of this they'll pay out of pocket. That's the left side of the O average. And the right side is the principal on a loan they have to take out. And interest compounds on that as well. So after we created it, we decided to test it over 4 different factors. These were household income, type of college, whether or not community college was used, and the size of the household. So 36 conditions in total. And the general trend we see is that the middle income bracket in our testing generally pay the most. This is probably because they don't qualify for as much financial aid, but they still have to take more loans out because they can't afford to pay it all out of pocket.
And so the interest on the loans add up. And also, looking at the 2 free years of community college, the cost is less than half, and this is again because of interest on loans. So after testing our model, we decided to look at which factors impacted the most. And this ended up being tuition. A 10% change in tuition led to about 20% change at most in the cost for a family. And this is because of, again, interest on loans. It builds up over time. And so now Alex Lee will talk about part 2 of our model.
Thank you, Vinay. So for part 2 of our model, whereas part 1 focused more on quantifying the cost, part 2 really focused on determining the benefit. So going in, we made several key assumptions, and one of them is the 50-30-20 rule of financing. And this is just a rule of thumb that governs how people generally spend their money. Usually people use 50% of their income on necessities, and then of the remaining 30% goes to everyday buying stuff, and 20% people usually invest or save up for later. And we also assume that income increases at a constant rate, and this was a simplifying assumption that we had to make because we couldn't find year-by-year data on how people get salary raises. But we later found out that this is a pretty accurate reflection of how people's income increases, so this assumption is relatively sound. So in designing our model, we developed a metric for the net financial benefit that people have accumulated each year. And this takes into account financial stability, which includes how many assets you have and your employment status, as well as how much income that you can spend or save. And we multiply this term by 0.5 to account for the 50-30-20 rule, where half of your income is spendable or savable. So before delving into the details of the terms of our financial benefit metric, one thing that we decided to calculate first was the assets that one has accumulated. And we developed a recursive equation for this because your assets build on what you already have on a yearly basis. So we multiply this additive term here by 0.2, and again, this is governed by the 50-30-20 rule, where 20% of one's earnings are saved. So for financial stability, we multiplied the probability of being employed, as well as the fraction of your spendable or savable income that your accumulated assets take up. So again, we have this 50% here to follow the 50-30-20 rule. So putting it all together, the algebra works out to this fairly simple equation for expected financial benefit. And this is pretty intuitive because you can think of it as the expected value of the amount of assets that one is expected to have in a given year. So finally, we end up with this coupled set of recurrence relations where we can take the accumulated assets from the first equation and then just plug it in to the financial benefit to obtain financial benefit as a function of years past. So in testing our model, we obtained values for income as well as debt from the US Census and Part 1 of our model respectively. And we tested the various degree options. So we see here, initially there's this dip in the curves, and is most pronounced for people who go through 4 years of STEM. And this makes sense because they have initially more debt and less income a few years after college or after high school. But then we see 10 years down the road that there's this intersection where the STEM path intersects the other paths, and after which they clearly dominate the other ones. And this makes sense because higher income comes from STEM jobs. And interestingly, we also note that 15 years after high school, even the non-STEM option for 4 years of undergrad surpasses high school. So this goes to show that regardless of whether you do STEM or not, although STEM is preferable, going to college is always worth it in the long run. And once you pay off your debt, you're going to be set for the rest of your life, and you're always going to do better than if you just go to high school. So now Graham is going to talk about part 3 of our model.
Thanks, Alex. So for part 3, we really wanted to get away from just looking at it from a financial standpoint, and we wanted to take the question of is college worth it in sort of a more holistic direction. We wanted to consider everything holistically. And we wanted to look at all the factors, so not just your finances, but also are you going to be happy? And so we sort of had to define what is happy to us. And we decided upon 6 factors that we thought were most important to your happiness. And those are, as you can see, the amount of time you can spend with your family, the amount of money you would earn, the amount of free time you'd have, the impact you could have on the world, your education level, and the amount of ambition that you have as a person. And also, it's important to note that we only considered the undergraduate level of education because once you start dealing with the cost of graduate school, you start dealing with different costs, and it gets too complex too quickly. So as we said earlier, we used a voting and game theory approach, and from voting theory, we used the idea of a board account. So say you have 5 kids in Manhattan, and they're trying to decide where to go for lunch. Well, they can each rank it, and then as you can see, we can assign points, and for this example, we get Wendy's as the ideal place for them to eat. Now, 5 people answering one question, that doesn't really help us. But what if we had one person answering 5 questions? Now that might help us. So we decided to make this survey where we take 3 traits at a time out of our 6 traits, and we have them rank them against one another. So that way we can accrue points from this survey, and we can create a matrix that sort of shows what the student cares about. And at the bottom, we can see an example matrix. The next idea that we had was this idea of a key matrix. Sort of how did these 6 factors that we determined focused on happiness, how do they deal with the different career paths? How are they associated with them? And so we can see, for example, the amount of free time you'd have. Sort of, if you're in college and an undergraduate degree in STEM, you don't have that much free time. But if you're in high school, you probably do. Or if you just get a high school degree, you'll probably have more free time. So this is sort of showing how these traits are associated with the different career paths. And the next thing we did was we created a payoff matrix. And how we did this was we divided all of the values in the student matrix by the maximum value. And so that way they're all relative to one another. And then we took each element and multiplied it by the element in the key matrix. So that way we have sort of the adjusted matrix for that student. And from this, it's important to note that we only considered the top 2 factors because with 2 factors you're dealing with lines, with 3 factors you deal with planes, and for each factor you add another level of complexity. And so we can create lines from this payoff matrix by assuming you only care about the first trait with probability Q and the second trait with probability 1 minus Q. And so we get these lines here and they're graphed in this diagram. And so we're looking for the highest expected value because that maximizes your happiness. And we find that that Nash equilibrium is between the path of high school and community college and undergraduate education in STEM. So these are 2 pretty disparate levels of education, to be sure. So what we had to decide upon was a third arbitrating factor that would really give more of a definitive answer of which path you should look into choosing. And we decided, what better than education? So the more education you have, you'll feel more fulfilled if you value it highly. So if you have a value greater than 15, we suggest that you go with the highest educational path that you have, because that way you'll feel more fulfilled in life and you'll be happier at the end of the day. And so for this example student, we'd encourage them to look at going to community college for 2 years and then transferring into a 4-year program in a STEM field. So now that we've sort of broken it down for you, I'm going to let Keshav help you guys put it back together.
Thank you, Graham. So for all 3 parts of our model, one thing we wanted to keep in mind was that we wanted everything that we did to be completely personalized to an individual. We wanted a different result for each person because every single person is going to value a college education differently. So for part 1, we had many different factors that go into a college education cost, like family size and family income. And we had this nice simple equation that allows us to accurately calculate the cost of college. And in part 2, we had another simple equation where you can just enter in a couple of different aspects of a career that you're considering, and you can see how beneficial those different career paths will be to you financially. So if you're considering a couple of different careers, you can just plug in this information and you can see which one monetarily will be the best. And in part 3, we looked at everything besides money and had a holistic view where somebody can just take a simple 20-question survey and we can figure out what is probably the best path for them to take. We believe that this personalized approach is probably the greatest strength of our model, and also the fact that it's very linear. All the equations are simple and easy to understand. Other people who come and haven't had as much experience with our model as we have can just use every single piece and have a better understanding of what's going on so that they understand what's going on in our model. There is a lot of data that's involved in college costs and things like that. So we had to make a couple of simplifying assumptions like unemployment rate and income rate. And also we could only consider the undergraduate level of education simply because graduate levels have different lengths and different costs and things like that, and it became out of the scope of our problem. So rather than trying to figure out different rates at which things increase, another thing we could do would be to scale down our model to a single college or a single area where STEM is a rapidly growing field so that people in that area can have a better understanding of what STEM would be like to that area that they live in. And also using a computational approach called Brown's algorithm, we can figure out what's the best career path for them in part 3, using all 6 traits or even more traits if we so chose to add more. Now, we'd like to thank Dr. Dan Teague and Ms. Christine Belladin for everything that they've done in advising us through this challenge. We'd also like to thank the Moody's Foundation and SIAM for giving us this unique opportunity. Thank you guys so much, and we are opening up for questions now.
Rachel?
So could someone flip back to the very last graph that you showed?
Right. Okay. Oh, on right. Go.
So if you were talking about your model with someone who isn't particularly mathematically focused, and you wanted to explain to them how to read these lines and then the importance of the intersections between the lines, how would you talk to them about what they're seeing here?
So these lines basically represent values. In game theory, the way things work is that in one iteration of a game, you get a certain amount of values for the strategy that you pick. So if you, in our example, in our equations, if I can flip back, so if you valued family Q with probability Q of the time, you would be picking family in a game if you played this game multiple times, Q percentage of the time. And after a while, you get this graph of possible values within the game that you can possibly have. You can't go above any of these lines. You can't go below any of these lines. So the dotted line that you see is basically the level that's the safest level. If you were to use a certain probability of family and a certain probability for money, then you can expect this horizontal line where no matter what you do, you're going to expect this level of happiness that we've determined. And
It's also important to note that sort of the values in the game are meaningless except unless they're relative to one another. So if you can flip back a slide. So this value of 10/3 for high school and family, that doesn't really mean anything unless it's relative to the other ones, because we're looking to maximize the expected value, because when you play a game against life, you don't necessarily get values from life. It's sort of, you want to maximize your value that you can get. So I think that's important to note as well.
So what does it mean when a line goes up
It means that
versus a line goes down?
So when a line, so as you go across the horizontal axis, it basically means you're picking the family strategy more percentage of the time. And as you go towards 0, you're picking the money more percentage of the time. So the horizontal axis is just the value of Q. So basically, if that line wasn't horizontal and it was, say, just with a positive slope, you could expect anything on that expected value, but that would mean sometimes you might end up with a poorer happiness level and sometimes you can end up with an even better value. So what we wanted to do was just make sure that you know exactly how much happiness you're going to be getting out of this. And that's really what we're trying to find, a stable point, not some kind of range of happiness.
Yeah. I have a question on your wealth equation. Can you bring that up?
In part 1?
Yes.
Okay,
Or no, part 2.
2. Let's see. Oh. Hello.
Keep going. That one.
Assets.
Here, did you consider here the gains you'd get from your investments, like capital gains or interest. Here it looks like you're just accumulating wealth from your savings.
I think most investments probably take up, are probably in a wider range. It would take too much to figure out exactly what kind of range an asset or some kind of investment would increase for this model in the time that we had allotted.
I might also want to add that even if we account for, so we tried to make some simplifying assumptions and making a simpler equation, but it is definitely possible for us to incorporate something that accounts for gains from investments, but that we do not believe that will change the general trend of our eventual results, because people with more income are going to invest more money. So it's just going to accentuate the difference between getting a STEM degree and not getting one.
A question, I think maybe to combine a few of these things, in particular to focus on your emphasis of personalization you had in your model. How would you factor in an individual's likelihood for success in their chosen area into your model, or throughout your model?
So I think part of it was, a small portion of it was addressed in part 2 when we included the unemployment rate. Things like that. We can always add more terms to consider things like how stable the job market is and how likely your salary is to increase over time, things like that. So although we didn't factor in those things as in depth as we could have, there's always room to add those things in our part 2.
Thank you very much.